face masks in class. I hate it. Everybody hates it, but we just got another email today that somebody tweeted that classes weren't observing the proper protocols, and so we just need to make sure we're doing that. Appreciate it. Huh? You are? Good. Is it loud enough? Yeah, I think the trick is I have to click off and then back on again. Yeah, I hear it. It's going to be delayed. So if you're in here, Zoom is delayed, I don't know, by a half of a second. You're welcome to wear earphones and zoom in. If you can hear me fine in here, the air handler is a little loud, but I'll try to talk up. If you can hear me fine, you don't have to be zoomed in. And the Zoom experience is mainly for people that might end up quarantined at home. It's not intended to be a replacement for attending class on a regular basis. I understand there's going to be cases where people have to stay home for various reasons, and that's fine. But I can't guarantee the Zoom is always going to work. You never know, and I'm not a video production company, so I do my best to provide that as best I can. The way I'm going to teach this class, I think mainly I'm going to have notes that I scan in and I put on the board on the screens, because I think that's a little clearer than me trying to write a lot of the long equations that we need for this class on the board, and the resolution for the camera is not as good as we need to do that kind of thing. So we'll see how it goes. I'm going to modify things as we go along, so I'd welcome feedback from anybody saying, hey, I don't like the screen, I don't like the way it looks, whatever. Just don't comment on my hair. I love the poster. If you look on the door of the lab next door, it's got the COVID poster, and it says, if you've got a fever or a cough or this or bad hair, don't come to work. It's a joke, of course. I'm Dr. Steck. I recognize a lot of you from earlier classes. But this is AE 714, and let me share my screen with what I'm going to put on the board. So this is the syllabus. It's online. My office is in 218 Wallace Hall, and I will have normal office hours where you can come in wearing a mask and sit across the room from me, and we'll social distance and you can see me in person. By appointment, if you need to Zoom via office hours, send me an email, and that way I can launch the Zoom at a certain time and we'll connect up that way. So we'll see how that goes. We may have to change that. It's the first time I've done this kind of hybrid stuff. Last semester I did office hours via Zoom at certain times, and like 3 or 4 people would just come and Zoom in and then sit there and look at me just to see what was going on. And that's fine, except that it really is reserved if you have a question or a comment, or you need to talk to me. My email is james.steck@wichita.edu. We do have a textbook for this class, and it's Airplane Flight Dynamics and Automatic Flight Controls. Fortunately, it's not real expensive, right? I think it's $70, either on Amazon or through the company in Lawrence. We do use this. We use it a lot, and I expect you to read along as we go through the class. And we especially use, in the back of the book, there's a whole bunch of airplanes and data on airplanes. We use those a lot. So you'll need those in the back as well as the material in the book. So make sure you get a copy of that. And so that's in the syllabus here. You should have a prerequisite, which is an undergrad flight dynamics and controls class. This class would be difficult to have if you haven't had something like that. You guys know the weird schedule we have this semester, right? We're beginning on time, no fall break. but we go online after Thanksgiving break. So Thanksgiving break starts on the Saturday before Thanksgiving. And then we'll have 1 week after that of online instruction and assignments. And then there'll be a final online the next week during the normal finals time. Homework, typically I collect homework hard copy in person in class, but I want to minimize papers going back and forth between you and me and between each other. And so I want you to scan your homework and submit it, upload it to Blackboard. Everybody, I'm sure, has done that last semester, right? There's apps on your phone. If you don't have a scanner at home, there's a bunch of apps you can get to put on your phone where you take pictures and scan it. I do need you to upload it, like if you have a homework number 1, which I need to put upload, make it a single file with your solutions. In other words, scan it, convert it to a PDF, and make it one PDF file. Because if it comes in as like 5 different images for the homework into Blackboard, then it's difficult for me to have to go through and click on each one of those and open them up and print them out or do whatever I'm going to do with it. So give me one file, PDF, of your homework. And as always, make sure you write legibly, especially now because it's harder to see on a computer. Make sure you space out your work, make it neat, and make it obvious where the problem starts and stops and what your solutions are. So that's homework policy. We are going to have, I was going to do my normal 3-hour-long exams in here, and I rethought that, looking at the schedule. And so we're going to go with 4 30-minute exams during the semester, spaced out. I think that will facilitate us being able to do that and then do some lecturing after that so that we're not locked into an entire class period for an exam, and it helps space it out. I think it's more of a quiz structure in that way. There's a final, and then homework, and there's flight test assignments that I've been doing for the last, I guess, 3 years. A grad student who works for Bombardier as a flight test engineer created these, and he will be coming in here and showing you how to do those and walking you through that. If you're thinking you're going to go up and fly an airplane, unfortunately, no. Although that'd be fun. These are done in X-Plane Flight Simulator. And typically I do this in teams of 2, and I think we can figure out a way to do that where you can get together with one other person and still maintain social distance and do these assignments. And those assignments will actually be done in here on the computers on this table. They all have the flight software on them. And you can see they have joysticks and throttle quadrants. So you'll schedule time to come in here and fly these assignments. It's not real arduous. It does take a little bit of time. But it gives you experience in what happens when they're trying to certify an actual airplane. And it should be fun. Don't stress out if you're not getting perfect answers, because it's difficult sometimes to fly those points. Do the best you can, record the data, and you'll get credit. So that's a fun addition that we've added to this class in the last couple of years, mainly due to his experience at working out at Bombardier as well as being a grad student here. All right, questions up to that point? Are you guys hearing any audio through the speakers in the ceiling? See, I don't know if that's a good thing or not. If I crank it up too far, then I start getting feedback and echo. Am I echoing yet? Are you hearing anything? The computer what? I'm trying to get it to come out these things in the ceiling, but if you're not hearing anything, I'm not going to mess with it. All right. I was hoping that we could get audio through that. Maybe we will on somebody that's on Zoom if they say something and ask a question. Are you still on Zoom? You don't have a microphone.
Can you hear me?
Yeah.
I'm
That's
here.
you? So it works. I guess it's not echoing me because otherwise we would get a lot of feedback. So let me crank it up a little bit more. Okay. No questions on the policies and procedures of the class. If you come up across issues, just shoot me an email. Again, I put the information about how the class would go. We're going up to Thanksgiving, then we're online. And then you can read the rest of this syllabus. Here's a tentative outline for the class. It's not guaranteed that we'll have exam number 1 on the 15th. It'll be pretty close to that day. It will depend upon where we are in completing homework and lecturing in the class. But those dates are going to be pretty close. And again, there's sections in the book. I encourage you to read the book. The book is very good. It's been around for a while, but it's written by Jan Roscom, who was a professor a long time at KU and taught flight dynamics and controls all his life. All right. So let me pull up the next screen that we need here. All right, you guys remember this from AE 514 if you took 514 from me? Does that look familiar? So I want you on your piece of paper, on your notes, to draw. You don't have to get the airplane looking that good, but draw that. And then on the diagram where you see the arrows, put the labels for the forces and the moments here and here. And the arrows there, label the axes first, X, Y, Z. And then label the forward force X. I'm forgetting one thing. Let me look at my notes. Yeah, so label the axes X, Y, Z all the way on the end of the axis. And then label the linear velocities U, V, and W. And I'll show you the answers here in a minute. And then label the angular velocities P, Q, and R on those circles there. And then also label roll, pitch, and yawing moments on those. So did everybody get that? You should have a little x, a little y, and a little z. You should have a u, a v, and a w for forward velocity, so on. Then you should have L, M, and N for the moments, and then P, Q, and R for the rotational rates. Is everybody good? All right. So here's what you should have. Now there's an extra information, the Z, the X, Y, and Z are the forces, but I didn't have you put those on there. Is everybody at a place where they can see this, one of the other screens pretty well? Is clear enough? All right, so this is what we've been talking about here. We have linear velocities. The velocity vector is U, I, V, J, W, K. That's forward, side, and vertical velocity. And by the way, since I've already written this down, usually I write this on the board, so it takes longer. So if I get ahead, raise your hand and say, slow down. Either that or we'll be done with the class halfway through the semester and we won't know what to do. And then the angular velocity vector omega is pi, qj, r, k. That's essentially what we drew on the diagram. And then the forces are x, y, and z, are sometimes called fx, fy, and fz. And then we have the rolling, pitching, and yawing moments, lm and n. And then we have the usual definitions of angle of attack and side slip angle, beta. Yeah, what do you need? And I could potentially zoom in a little bigger, but I'd want to make sure that we get a significant part on the screen. We don't need. Are we good? So we're going to define alpha and beta, and so that's on the next page. So if you look at a top, start with the right figure here. So that's where we need to start. There's the full velocity vector forward with some side velocity v. And then you see the other two components, the x and the z component, both in this plane here. And hang on a second, let me see if I can make my cursor bigger. Yeah. All right, let's see how we're doing now. All right, I think that's easier to see. So we've got the velocity vector here, the side velocity v, so this angle is beta. And so the sine of beta is little v over the magnitude of the full vector v, right? And then if you look at the side of the airplane, then you can see the two components that were hidden in that vertical plane, the u, forward velocity, and the downward velocity w. And so alpha is the tangent of those two. So are we good? Usually I can look around and see if people are still writing, but it's a little harder in this room. And a lot of the figures that I show on the board and diagrams are in your book as well. But I encourage you to do what you're doing now and write them down, because I think you process it differently if you actually do it. You keep your attention on the class, hopefully, and you get less bored and more engaged. All right, can I put this off the screen now? Anybody still getting this down? We're good? All right, the last thing that we'll use, and that is really washed out. Can you see that? It's what we call longitudinal motion and lateral directional motion. Longitudinal is U and W and Q. And lateral directional motion is P, R, and V. So really this is motion in the vertical plane and pitch. And then lateral directional is anything outside that vertical plane. So roll, yaw, pushes the nose outside of the plane, or the wings outside the plane motion. And then side velocity is out of the plane because you're moving the airplane across the plane. And you've seen this before in your undergrad classes, just a reminder, because we can separate out the analysis into longitudinal and lateral directional, and it makes things a lot easier. All right, so we've done all this. And this is a diagram that kind of outlines the first half of the class. Chapter 1 is going to be the equations of motion, where you put in the forces and moments, and then you calculate the motion. Altitude, pitch rate, this is longitudinal, the velocities here, and accelerations. So chapter 1, we'll be talking about essentially Newton's laws for the airplane. So we'll spend 2 weeks, 2.5 weeks on that. And then chapters 2 and 3 are talking about how do you calculate the forces and the moments. Because the elevator produces a force, it also produces a moment. Flaps, throttle, produce forces and moments. So essentially we're going to calculate lift and drag and pitching moment and then put them in the proper axes. And then we'll also talk about the full equations of motion occasionally, where you have elevator, flap, thrust, aileron, rudder, spoilers, and you get the 3 forces, the 3 moments, and it goes into the full-blown equations of motion that are not separated out into longitudinal and lateral directional, and you calculate the motion of the aircraft. And you don't need to copy this down. It's just information about, well, I'll show you some block diagrams as we go along in MATLAB that do this kind of thing. All right, questions so far? This is kind of an introduction and a reminder of stuff we knew in 514. Feedback? Is this working? Again, I'd rather be writing on the board, but this is the next best thing, I think, for this environment. If you have any ideas about how to change things up and make it more interesting, let me know. Okay, so chapter 1 is the equations of motion. And I'd say that chapter 1 and the lecture we're going to do next time is probably the most tedious that we'll do here. In your dynamics class, you looked at the equations of motion for a distributed body, right? Newton's law is for a point mass. But if we have a disk, then we need to apply Newton's law to all of the little tiny point masses on that disk. And so, I guess I won't write on the board. We got a picture here, but actually I am. So let me stop the sharing here for a second. Well, now I did it. Okay. There we go. So the idea here is that on any kind of a rigid body, we can attach a body fixed axis system like that. But it's not a point mass. And so we have to look at the forces and moments on each little point mass dm. And we have to do that relative to another axis system that's inertial, because this body can be rotating. And so the diagram that I'll pull up here in a minute, but I wanted to walk through it before we looked at the whole thing, is that we have to look at how each little point mass via a position vector moves in this axis system, the inertial reference frame. And so essentially we end up integrating all of these little masses and Newton's law applied to each of those masses over the whole airplane. And the picture that I'm going to show you is my sketch. It's not the greatest, so there is a version of that in your book that you can look up as well. It's much better because they took a lot of time drawing it. But what we're going to do is write the force equation for Newton's law and then also the moment equation. And this one's not too bad, but this one gets complicated. And you've essentially gone through some form of this in AE 223. No, what's dynamics? Gosh, I've lost it. You guys should know. Dynamics. Okay, we'll call it that. 223, I think, is statics, right? Anyway. So in dynamics, you did this probably for a disk. And you end up with like the moments of inertia of the disk, like IXX, IYY, IZZ, right? So we're going to go back to square one and go through the whole thing here again, just for completeness and so that you understand, you've seen it again. It may come in handy. I had a grad student who wanted to do something with an airplane where the wing fell off. And so obviously if the wing falls off, the inertias all change. And so he wanted to simulate that within the equations of motion. So he went back and derived the equations again for a mass moving or shifting. All right, so I'm going to go back to this. Let me share my screen. And this diagram over here, although it's scanned in a bit faint, is this diagram that I'm showing on the screen, and it's also a diagram in the book. There's an inertial reference frame, O, an X prime, Y prime, Z prime axis. And then the airplane is located up here in an X and a Y and a Z body fixed axis. So there's an inertial frame and a body fixed frame. And then we look at each little mass element, and there's a vector R prime that points to it from O. And then we track also with a vector RP that goes from the origin to some arbitrary point P on the airplane. And then we can track the mass relative to P with this vector R. And it's going to turn out that this point P will become very important if we choose it properly. It'll simplify things a lot. So the idea here is that the forces act on the area here. So that's like pressure, right? Force per unit area acts on this little element ds. It has a volume dv, so if you multiply by the density, you get the mass. And in fact, we can integrate over the whole airplane this dm, and we could calculate the total mass of the airplane, right? And every once in a while, it's good to remind yourself that integration is really just adding up small pieces, right? It's a limit of a summation. And then the gravitational force on this is going to be g times little dm. And so those are the forces that are applied to that little element. And then we add up all those forces and we get Newton's law for a rigid body. So this is just repeating what I said up there. dm is rho dv. Local mass density of the aircraft is rho. Gravitational force is gravity times dm. And the aerodynamic and thrust forces are this F thing. And we do them per unit area. So we can get the total force on the airplane by integrating all of the pressure around the aircraft. So this is the basis for forming Newton's law. So again, we have to do Newton's law in this inertial reference frame, which is the O-axis. And it's really just sum of the forces as d by dt of the linear momentum. So the forces are gravity integrated over the entire volume. Pressure forces integrated over the surface. And then d by dt of the linear momentum, which is mass times velocity. And that's the force equation. So I encourage you to write that down. So this is nothing new. It's Newton's law for each little mass element, and we just integrate over the whole airplane. All right, and then you know the definition of moment, right? It's r cross a force. That gives you a moment. So that equation that's at the bottom of the screen there, we're just going to take r, which is that vector from O to dm, crossed with that, and that's going to give us a moment. So that's on the next page. So let me know when you're finished writing this equation down. Is everybody good? Because the next equation is just going to be r cross that inside each of the integrals. So I think I can get both of those on the screen at the same time. So this is sum of the moments is d by t of the angular momentum, or it's really just r prime. That's the vector from O to the dm crossed with each of the forces and the moment. So this is angular momentum is r cross linear momentum. Angular moments are r cross forces, gravity, and so on. So I'll give you a minute to write that down. And so you'd think we'd be done, and we are, except that it's very difficult to handle all of the terms in this equation relative to this inertial coordinate frame. It'd be nice if instead of doing these integrals in that external Earth fixed frame, we could do it on board the airplane. Because no matter what the orientation of the airplane is, whether it's pitching up or pitching down, all of the mass elements are in the same spot in that body fixed axis system. But in this Earth fixed axis system, if the airplane's climbing, the nose is up. If the airplane's diving, the nose is down. And so you have to keep track of that inside these equations of motion all the time. So everybody, for good reason, is you convert it to a body fixed axis system XYZ. So that's what we're going to do for the rest of today and then next time. And the force equation is not bad, but the moment equation takes some work. And there's some key assumptions we're going to make. And write this one down in big letters. We're going to assume we have a rigid aircraft. So if the airplane is rigid, that means each mass element stays relative to the XYZ axis in the same spot. If the wings are flapping up and down, the wingtips change with time, right? But if it's rigid, that wingtip is always out at the same spot on the y-axis. And so this volume integral can be done one time for that rigid airplane, and then we're done. And in fact, that makes it really easy, right? We don't have to keep track of each mass element. We just add them all up and call that the total mass, M. So you can see how even right now it makes the calculations of those integrals easy. And that's why people do this. It also means the derivatives of the density with respect to time are 0. So you go, yeah, well, what about the fuel in the fuel tanks burning? Because that mass is changing, right? So we're neglecting that. We're saying we're not looking at a flight across the Atlantic. We're looking at maybe a 5-minute flight where the fuel volume is pretty much constant and the mass is constant. So the next step is what I was talking about. It's easier to deal with the aircraft geometry in terms of the vectors r and rp prime. So rp prime is the vector from the origin to that point P on the airplane, and then r is the little vector on the airplane. Sorry, what? Yeah. So again, the key assumptions here are rigid aircraft and the mass is not changing with time. So if you get to a job and they're having you do performance or some other kind of calculations where there's a significant change in mass, I don't know, maybe we're not doing airplanes, we're doing satellites, and the rocket blasts off, right? And then it drops off the first stage. It's a big change in mass. So the equations have to account for that. But for aircraft, we're not going to do that. This would also mean that if you drop a bomb, you have to account for that. These equations would not necessarily hold completely for those cases. So no bomb dropping in this class, no second stage launches. So we're just talking about a rigid airplane. Okay, can I go on? Anybody else? All right, so what we're going to do is everywhere we see r in the equation on this page, that's the one I had you write down. Oh, sorry, not the moment equation. We're doing the force equation. Everywhere you see r, we're going to put rp plus little r. And that's why the force equation is so easy, because r only shows up one spot. You can imagine the moment equation is going to be a little harder because here's r, here's r, here's r, and here's r. But we're going to not do that one today. So we plug in rp plus r. And then we separate out these two integral terms. So I'll give you a minute to write this down. So really all you're doing is making the substitution and then splitting that integral into the sum of two integrals. And we can pull rp out because rp doesn't depend upon dv. rp is that point P is fixed on the airplane. It does not depend upon which little mass element we're looking at. And then we're going to look at this and say, well, gee, that's just the total mass. Because we said we have a rigid airplane, we can pre-calculate this. So why leave the integral there? We're just going to call it m. So this is mass times gravity. Makes sense. That's a force on the airplane. And then we're going to say, well, we can calculate the total lift of the airplane by integrating over all of the surface area of the wing and the fuselage and calculate an aerodynamic force. So we're not going to leave this integral in there. We're going to say, well, the aerodynamicists are going to tell us what the aerodynamic forces are. And then the propulsion people are going to tell us what the thrust forces are from the engine. So far, so good. And then over here, we've split out the RP prime, pulled it out, and then we look at this and we go, well, this is just the total mass here. That's nice. This is mass times the change with respect to time of the velocity of point P. So that's just mass times acceleration. This is starting to look real familiar. And so what about this term here? That looks really complicated. So I need to go to the next page. So d by dt of r, that's just the change with respect to time of that position vector, so that's just vp. And then d by dt of velocity is acceleration, so we're good there. And then this term here, this says the integral of the mass. Let's go to the next page. Are we good? Anybody still working on those others? And again, I encourage you to write this stuff down like you normally would if I'm writing on the blackboard, because it keeps you engaged. All right, so what we need to think about now is, well, what is this term? This is the density times each little dm. So let's look at a real simple case. Let's not look at an airplane. Let's look at this picture right here. There's the point P. And what if we have a kilogram mass over here, like on a barbell, and another kilogram mass over here? And they're each 1 meter away from the center point P. And then we do this integral. This says, well, we have to add up this positive distance 1 meter over here times 1 kilogram. And then we have to add up this negative distance over here times 1 kilogram. And what do I get? Positive 1 plus negative 1 gives me what? 0 if the point P is in the middle of these two masses. So the key here is we're going to choose the point P, which is initially arbitrary, to be the center of mass or the center of gravity. So that's another assumption you need to write down, is that we deliberately choose the point on the airplane that we do our calculations about to be the center of mass. And this is the real reason why in dynamics you always talk about the center of mass of an object when you're doing dynamics, is because that collapses terms down, makes the equations a lot easier. There's no reason why you can't do dynamics or flight dynamics choosing a different point P. It just gets a lot more complicated. And again, you've seen this before and you've talked about it. You know the center of gravity, center of mass is important. You've seen that in dynamics. This is just a reminder. And so this integral is 0 because we'll define P to be the center of mass. And so the force equation now comes out to be what you would have said, well, I knew that already from dynamics, is that the sum of the forces equals the mass times the acceleration. But it's important, especially with the moment equation, to see why that choice is so critical. Otherwise, we get a giant mess. And then
the last thing we're going to do is transform from the inertial reference frame to the body fixed XYZ reference frame, because it's so much easier to calculate lift, drag, and pitching moment in that body fixed axis. Lift is up, drag is back, thrust is forward. Whereas in the earth fixed axis system, you have to keep track of the orientation of the aircraft relative to the earth. The only thing that gets harder is which direction gravity acts. In the earth fixed axis, gravity always acts down. So we'll have to transform the gravity vector to fit the body fixed axis system. Because if the airplane's going straight up, gravity acts backward, right? If the airplane's flying level, gravity acts downward. All right, so really all we do is take the vectors of forces and transform them. We put an XYZ on the bottom so that we say now we're in the XYZ axis. And by the way, we're going to drop writing the XYZ from now on and just assume that we're always in the body fixed axis system, because we're going to be calling it the body fixed axis equations of motion. The only tricky part is that if you have an axis system XYZ that's rotating, then the derivatives have to be adjusted. So here's the derivative of a vector A in the inertial reference frame. And here's what you have to do if the body is rotating with an angular velocity omega. And this is where you start talking about centripetal acceleration and all of that stuff. It's really, this is the derivative term, this is a centripetal term. And so to take the derivative that we have in our equation, the dv by dt, we have to do a dv by dt plus omega cross v in order to get that. So once we realize we have to do this, then here is the force equations of motion right here. And it's important that we highlight this, because this is what we'll use for the dynamics of the airplane. So the last piece that we need to do on this equation before we quit is we have to take this cross product here. Because everything else is just stuffing in vectors. So we'll have to calculate that cross product. But first, how are we doing on time? 4:55. So give me another 10 minutes and we'll call it good. Is everybody caught up? Let me give you a second. Do I need to go back up at all? I need to think about that. I guess I'm a bit biased against doing that for multiple reasons. I remember a class that I took where the instructor posted the notes and you just kind of filled in the blank as you went along, and you tended to not pay attention in class as much. But I'll think about it since we're in weird times here.
It's difficult to write things down when you're doing with your mouse, trying to follow the mouse.
Yeah. So that's why I'm willing to slow down as much as I need to. Does anybody need me to back up? Please say something. Don't hesitate. Don't be shy. Please ask, because everybody, including me, are trying to give you the best experience possible given the circumstances. Anybody need to write something down further up? I'm happy to go back because we're ahead today. And I will try to give you a heads up. All of this stuff is in the book. If there's a lecture that I give that goes outside of what's in the book, I'll tell you, and there are several of those during the semester. So I'll try to say, heads up, this is not in the book, make sure you get it written down. While we're waiting, does everybody have access to MATLAB? Like, you guys all buy student versions of it? I mean, MATLAB's available in here, but sometimes it's just, you know, if you're trying to work from home. You guys have all used MATLAB, right? 227, other classes. So the downside I found to this whole deal is we have to wear a mask, right? The upside is it seems like I can park whenever I want, anywhere I want, and there's spaces. Is that true in the student lots? Sort of, yeah. All right. Again, please say, can I see the previous page again if you need to? So this is not a derivation, but I want to convince you that this thing here is true. And so does it help if I actually turn on this pointer and write on the screen as I talk, or does that get in the way? I did that when I was doing online lectures recording because it kind of pointed to stuff, but I don't want to clutter it up. So the deal is in the Earth fixed axis system, this is a vector AX, AY, and AZ, is that those three things depend on time, but the unit vectors I, J, and K do not depend on time. Whereas if we have that same vector expressed in the body fixed axis system that's moving, then AX, AY, and AZ do depend on time, and I, J, and K, because they're the unit vectors in the axis, they're moving as well, and so that's where those extra terms come from. So if you look at taking the derivative of this thing down here, then you have to do the product rule. You have the derivative of AX with respect to time times I, and then AX times the derivative of I with respect to T. Same thing for J and K. And so these extra terms are what give you that cross product, the omega cross the vector. And so that's really all I want to do with the derivation. If you collect those terms together, that's what this is saying, is that's omega cross A. And if you go through a derivation, you can see that, for example, I, the vector I here, is changing due to Q and R, right? Q is making I go up, and R is making I go over. And P doesn't change I. And so that's why you get the cross product, is that Q and R are the J and K, so those cross products show up, and those change I, and in fact, that's what those terms are in the omega cross the vector. So again, I'm not trying to derive that. I'm just trying to say that these terms, if you go through a full derivation, you get that omega cross, because this vector I is changing due to Q and R. All right, so did I go too fast through that? Okay. This is what you need to write down. So an Earth fixed vector does not, the unit vectors don't change. In the body fixed axis, they do change. And really, this is just not a derivation, it's to convince you that it makes sense. Oh, I guess disclaimer or caveat or whatever, this page right here is not in the textbook. The formula omega cross V is, but this is my own little explanation. Yeah, my notation is not real great. It is, yeah, it's just a derivative. It should be not partial derivative. The book has its own special notation where it talks about the total derivative of a vector versus just the derivative, and it's kind of cumbersome. But I don't think my notation here is that much better because it's confusing partial derivatives with just not the total derivative. So should I scroll down part of the screen? I don't know if I should say this or not, but I realize that if you're zoomed in, you have an advantage. Do you know what that is? You do have the option to zoom in on your computers here. You could actually screenshot, right? But again, I encourage you to write it down. It's my own preference, but I think if you write it down, you pay attention and you process it a different way, it goes through a different part of your brain. And you see each individual term instead of just looking at it and go, oh yeah, I remember that. So it forces you to focus on the terms as you write them down, maybe. All right, so this down here, I don't want you to write. That's just reminding me on how to talk through I changing to the Q and R. If you want to write this part down, you can. But really, that's all it is you can look at this diagram and say Q and R, obviously change I. All right, we got 4 minutes to keep my promise that we'll be done in 10 minutes from when I said it. So what we're going to do, and I guess we're going to go maybe a few minutes over. What we need to do next is plug in the vectors here. And in fact, I'll tell you what, let's quit. This is not that big of a step, but let's save it for next time. And then we'll go on to the moment equation. So if you want to do this, because I'm going to give it to you to do next time, carry out this cross product. That's omega cross velocity, right? We need omega cross with VP. So if you want to do that when you go home and you're looking through your notes, carry out that cross product because everything else is easy. It's just derivatives and plugging in the vectors. So that cross product's the only thing we have to do to work on this. But I want to give you time to write it down and we'll do that fresh next time. So several people remember where we stopped. Because typically I will leave my notes open to that, but since we're doing this online with these online notes, I'll have to remember. So if you're reading the book, start reading chapter 1. It goes through this, and you can read ahead about the moment equation as well. All right, just curious, your other classes that you're taking, are any of them online totally? Are they engineering classes? So what do you have engineering that's online? Senior design is online. Are you doing projects and building airplanes? So you'll get together with your team, but not with the whole class. So you have an online class, but it's not engineering? Yeah. Okay.
Got flight dynamics and control. Data.
Oh, 607? Is that totally online?
Yeah. Well, yeah, doing it hybrid. So
Doing what?
we're in groups, so we'll come in small groups every other day. So it's also online.
Oh, so it's a hybrid because it's larger, yeah. We're fortunate with this class that this room is big enough that we can accommodate the whole class and get us all. That way we don't try to decide who comes in on what days. All right, let me know if there's anything I can do to make your experience better. Other than like serving coffee and drinks during class, although that might be fun, huh? All right, that's it for today. Thank you.
I don't know if there's any way to go slower. I mean, it's difficult to write things down there, jumping from point to point.
No, I understand, and I wish I could put one page on one screen and another page on another screen.
I'm
And
thinking of how I mean, if we could write the notes out before, talk about it. I mean, that's kind of what I did when we did last semester with flight dynamics. The class before this one. I would pause it, write everything down, and watch and see.
Oh, right, when it was recorded. Yeah.
I don't know if you could give us the notes before class, we could write them out, and then we can just kind of follow or make the comments that you make on
On the sheet. Yeah, let me think about that. I'll have to figure out how I can do that.
Did you like write the notes out virtually, like on OneNote, and just share your screen that way?
Yeah, see, I actually have a Dell computer, a tablet, and that's what I'm hoping to do.
Okay.
So this is more of a stopgap until it comes in, and we'll see how that works.
You know, also,
Because I'd really like to do that. That way I can write real time and it'll be projected. But it's too hard to sit here with the mouse and try to do that on this. So hopefully the touchscreen will do that.
okay. When do you think you'll have the Dell?
I don't know. I put in the purchase order on Friday, and Dell is backed up. They were promising it by the end of this week, but I don't know if the purchase order has gone in or not. So I'll do the best. As a stopgap, maybe I'll just go ahead and post these notes, and that way you guys can refer to them until we get going.
You recorded this lecture, right?
Yeah.
Okay, so we'll be able to.
Yep.
Thank you very much.
So I need to shut this down, in fact. Hang on a second.